When wiring a house without metal water pipes, it's important to understand the grounding requirements outlined in the National Electrical Code, or NEC. While driving two ground rods is a common practice, the NEC section 250.53 A6 specifies that the grounding electrode system shall include one or more of the following components: a water pipe system, a metal underground gas piping system, ground rods, a concrete encased electrode, and a plate electrode. Therefore, even with two ground rods, installing a supplemental ground electrode, such as a concrete encased electrode or a plate electrode, is highly recommended to enhance the grounding system and provide additional protection. There are several reasons why a supplemental ground electrode is beneficial. Firstly, increased grounding capacity. A concrete encased electrode or a plate electrode provides a larger surface area for grounding, which increases the overall grounding capacity and reduces the resistance to earth. Secondly, redundancy. Having multiple grounding electrodes creates redundancy and provides a backup in case one of the electrodes fails. Thirdly, improved safety. A supplemental electrode helps to create a more robust grounding system, which improves electrical safety by providing a reliable path for fault currents and lightning strikes. To install a concrete encased electrode, it should be at least 8 feet long and 2 inches in diameter, encased in concrete. Alternatively, a plate electrode should be at least 2 feet square and 0.6 inches thick. Connect the supplemental ground electrode to the grounding electrode system using a copper conductor sized according to the NEC. Proper grounding is essential for electrical safety. A well-designed grounding system helps to protect against electrical shock, equipment damage, and fire hazards. The grounding system provides a low impedance path for fault currents to flow back to the source, allowing overcurrent protection devices, such as circuit breakers or fuses, to quickly trip and de-energize the circuit. This helps to prevent dangerous voltage buildup and minimize the risk of electrical hazards. It's crucial to consult the NEC and local electrical codes for specific requirements and guidelines related to grounding. These codes provide detailed information on the proper sizing, installation, and connection of grounding electrodes and conductors. Adhering to these codes ensures that the grounding system meets the necessary safety standards and provides adequate protection. When selecting a supplemental grounding electrode, consider the soil conditions and the available space. Concrete encased electrodes are typically used in areas with high soil resistivity, as the concrete helps to improve the electrode's contact with the earth. Plate electrodes are suitable for areas with limited space or where driving ground rods is difficult. The size of the grounding conductor used to connect the supplemental electrode to the grounding electrode system is determined by the size of the service entrance conductors. The NEC provides tables that specify the minimum size of the grounding conductor based on the size of the service entrance conductors. It's important to use the correct size conductor to ensure that the grounding system can effectively carry fault currents. In addition to the grounding electrode system, other components of the grounding system include the grounding electrode conductor, the equipment grounding conductor, and the bonding jumpers. The grounding electrode conductor connects the grounding electrode system to the neutral bus in the service panel. The equipment grounding conductor provides a path for fault currents to flow back to the source from electrical equipment and appliances. Bonding jumpers are used to connect metal parts of the electrical system together, such as metal enclosures, raceways, and piping systems, to ensure that they are all at the same electrical potential. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness. Check the grounding electrodes and conductors for corrosion or damage. Verify that all connections are tight and secure. Test the grounding system using a ground resistance meter to ensure that it meets the required resistance levels. If any problems are found, take corrective action promptly to restore the grounding system to its proper operating condition. Remember that electrical work can be dangerous, and it's always best to consult with a qualified electrician if you're not comfortable performing the work yourself. A qualified electrician has the knowledge, skills, and experience to ensure that the electrical system is installed and maintained safely and correctly. The role of the grounding electrode system is crucial in providing a safe and reliable electrical system. It serves as a primary connection to the earth, providing a low impedance path for fault currents. This path allows overcurrent protection devices to quickly clear faults, minimizing the risk of electrical shock, equipment damage, and fire hazards. The grounding electrode system works in conjunction with other components of the grounding system, such as the grounding electrode conductor, the equipment grounding conductor, and bonding jumpers, to create a comprehensive safety net. These components work together to ensure that all metal parts of the electrical system are at the same electrical potential and that fault currents are safely routed back to the source. Regular inspection and maintenance of the grounding electrode system are essential to ensure its continued effectiveness. Over time, grounding electrodes can corrode or become damaged, which can increase the resistance of the grounding system. High resistance in the grounding system can impede the flow of fault currents, reducing the effectiveness of the overcurrent protection devices. Therefore, it's important to periodically inspect the grounding electrodes for signs of corrosion or damage and replace them if necessary. Connections to the grounding electrode should also be checked to ensure that they are tight and secure. Loose connections can also increase the resistance of the grounding system and reduce its effectiveness. In addition to visual inspections, the grounding electrode system should be tested using a ground resistance meter. A ground resistance meter measures the resistance of the grounding system to earth. The measured resistance should be within acceptable limits, as specified by the NEC and local electrical codes. If the resistance is too high, it indicates a problem with the grounding system that needs to be addressed. There are several factors that can affect the resistance of the grounding electrode system, including the type of soil, the moisture content of the soil, and the size and type of grounding electrodes. Soils with high moisture content typically have lower resistance than dry soils. Similarly, larger grounding electrodes typically have lower resistance than smaller electrodes. The type of soil also plays a role, with some soils being more conductive than others. When designing a grounding electrode system, it's important to consider these factors and select the appropriate grounding electrodes and installation methods to achieve the desired resistance level. In some cases, it may be necessary to install multiple grounding electrodes to achieve the required resistance. The NEC provides guidelines for the spacing and installation of multiple grounding electrodes. In addition to the grounding electrode system, bonding is another important aspect of electrical safety. Bonding involves connecting all metal parts of the electrical system together to create a common electrical potential. This includes metal enclosures, raceways, piping systems, and other metal parts that are likely to become energized. Bonding helps to prevent voltage differences between metal parts, which can create a shock hazard. When a fault occurs, the fault current flows through the bonding conductors back to the source, allowing the overcurrent protection devices to quickly clear the fault. The NEC provides detailed requirements for bonding, including the size and type of bonding conductors and the methods of making bonding connections. It's important to follow these requirements carefully to ensure that the bonding system is effective. Surge protection is another important consideration for electrical safety. Surges are transient overvoltages that can damage electrical equipment and appliances. Surges can be caused by lightning strikes, power line switching, or other electrical disturbances. Surge protective devices, or SPDs, are designed to protect electrical equipment from surges by diverting the surge current to ground. SPD are typically installed at the service entrance and at branch circuits to provide comprehensive surge protection. The NEC provides requirements for the installation of SPD, including the location, type, and rating of the SPD. It's important to select SPD that are appropriate for the application and to install them according to the manufacturer's instructions and the NEC requirements. Ground fault circuit interrupters, or GFCIs, are another important safety device that helps to protect against electrical shock. GFCIs are designed to detect ground faults, which are unintentional electrical paths between a live conductor and ground. When a ground fault is detected, the GFCI quickly trips the circuit, interrupting the flow of electricity and preventing electrical shock. GFCIs are required in certain locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. The NEC provides requirements for the installation of GFCIs, including the location and type of GFCIs. It's important to install GFCIs in accordance with the NEC requirements to ensure that they provide adequate protection. Arc fault circuit interrupters, RFCIs, are another type of circuit breaker that is designed to protect against electrical fires. RFCIs detect arc faults, which are dangerous electrical arcs that can occur in damaged or worn wiring. When an arc fault is detected, the RFCI quickly trips the circuit, interrupting the flow of electricity and preventing a fire. RFCIs are required in certain locations, such as bedrooms, living rooms, and dining rooms, where there is a high risk of electrical fires. The NEC provides requirements for the installation of RFCIs, including the location and type of RFCIs. It's important to install RFCIs in accordance with the NEC requirements to ensure that they provide adequate protection. In summary, a well-designed and properly installed grounding system is essential for electrical safety. The grounding system provides a low-impedance path for fault currents, allowing overcurrent protection devices to quickly clear faults and prevent electrical shock, equipment damage, and fire hazards. The grounding system should include a grounding electrode system, a grounding electrode conductor, equipment grounding conductors, and bonding jumpers. Regular inspection and maintenance of the grounding system are essential to ensure its continued effectiveness.